You deploy a perfectly optimized piece of code only to watch your entire platform grind to a halt. Why? Because optimizing one component in isolation is the fastest way to degrade the whole system. We take architectural shortcuts to hit deadlines, centralize teams for short term cost savings, and call it efficiency. But under the surface, we're just building a mountain of tech debt. Today, we're exploring why traditional reductionist thinking fails and how systems thinking is the only way to truly optimize your software architecture. Hi, I'm Jeremy, the Internet Scrum Master. I have over 20 years in software development and 10 years as a full-time Scrum Master. Thanks for tuning in. Let's dive into systems thinking. Foundations of system thinking in software engineering. The discipline of software engineering has undergone a profound structural shift, transitioning from a historical focus on localized, deterministic code authorship to the management of complex nonlinear systems. As software ecosystems scale to define global commerce and cloud infrastructure, traditional reductionist problem-solving models, which isolate individual components for analysis, fail to anticipate emergent system-wide behaviors, structural bottlenecks, and operational failures. Systems thinking addresses this complexity by viewing software systems as interconnected wholes, focusing analytical attention on the relationships, dynamics, and feedback loops, rather than on the isolated properties of the components themselves. This analytical framework traces its origins to the general systems theory of the late 1920s and was first operationalized within engineering by J. Forrester through systems dynamic modeling. Within contemporary software engineering research, systems thinking is recognized as a core competency for developing technological and engineering literacy. This shift is reflected in academic and professional frameworks where technological and engineering literacy gains are actively coupled with systems-oriented design and evaluation processes. For instance, specialized postgraduate curricula have evolved to integrate software architecture, digital innovation, and sustainability, utilizing makerspaces and collaborative studios to build systems thinking capabilities designed to resolve complex multi-domain challenges. In practice, software systems are categorized based on their structural clarity and boundary definitions. Well-defined systems represent simple, multi-domain systems characterized by direct, linear cause and effect relationships that are easily modeled and predicted. Ill-defined systems encompass complex systems of systems, cyber-physical human systems, and socio-technical humanitarian engineering environments. These environments exhibit emergence, where the behavior of the whole cannot be predicted from the behavior of its individual parts, alongside dynamic complexity and highly nonlinear relationships. To navigate these ill-defined environments, researchers utilize structured conceptual frameworks. Cabrea's DSRP theory operationalizes systems thinking through four fundamental cognitive patterns: distinctions, defining boundaries and identifying what is and is not part of the system; systems, organizing information into parts and wholes; relationships, tracing feedback loops and cause and effect connections; and perspectives, reframing the system through diverse stakeholder viewpoints. This is supplemented by the Monod and Gannon systems thinking research, analyzing popular systems thinking literature, and concluded that systems thinking provides a great deal of power and value. It can be used to solve complex problems that are not solvable using conventional reductionist thinking because it focuses on the relationships among system components as well as the components themselves. Those relationships often dominate system performance. Whole system optimization and software architecture design. Whole system optimization applies systems thinking directly to the design, evaluation, and operational maintenance of software architectures. The architectural design of a software system serves as a structural blueprint that defines components, interactions, and boundary constraints, facilitating the mitigation of technical risk, the seamless integration of new features, and alignment with organizational goals. System-wide quality attributes such as security, availability, and performance are fundamentally shaped by this architecture. To systematically guide and audit architecture reviews, particularly in legacy systems undergoing modernization, researchers utilize structured evaluation mechanisms. An extension of the software engineering method and theory kernel conceptualizes architecture evaluations across 5 essential alphas, which represent key dimensions of system health and progression. Each alpha progresses through a series of defined states to ensure that legacy system maintenance and modernization activities do not introduce structural degradation. When software systems grow in complexity, the design space, encompassing options for component selection, replication, hardware mapping, and network topologies, expands. This combination makes manual architecture optimization mathematically untenable. A landmark systematic literature review by Alti, I think that's how you pronounce it, which analyzed 188 optimization papers published across multiple software engineering journals and conferences, highlighted a major fragmentation in the research landscape. Historically, optimization activities have been isolated within separate system domains, such as embedded systems versus enterprise information systems, and focused on individual quality attributes, leading to redundant parallel research. To manage the mathematical complexity of design space exploration, traditional optimization models restricted the variability of architectural decisions by modifying only a single isolated aspect of the system. The synthesis of this fragmented literature has enabled the development of unified trade-off analysis frameworks. Modern methodologies such as surrogate-based architecture optimization and bridge model-based systems engineering approaches utilize open source simulation tools such as PyCycle and OpenMDAO to construct modular interfaces. This modularity allows engineers to tune the complexity of the optimization problem by dynamically varying the number of design variables, constraints, and objective functions, achieving optimal dual-band performance and structural balance across the entire system. Suboptimization and the theory of constraints. In direct opposition to systems thinking, local optimization, or suboptimization, occurs when individual functional departments, software components, or development tasks are optimized in isolation, resulting in a degradation of the overall system's performance. Suboptimization is frequently driven by bounded rationality, where decisions that are highly logical within the narrow context of a specific department or software subsystem are executed without understanding their broader systemic consequences. This functional isolation is common in organizations that centralize technology resources, such as shared services, centralized database management, or outsourced application development, to maximize local departmental efficiency. While centralization may produce short-term cost savings, it often creates severe operational silos and handoff delays, ultimately slowing down the overall value to the customer. To diagnose and resolve these systemic inefficiencies, researchers apply Goldratt's theory of constraints as an analytical tool within agile and lean software development lifecycles. The theory of constraints posits that every software engineering organization operates as a system of interconnected chains, tasks that must be completed in a specific sequence, and at any given point in time there's exactly one weakest link in the system bottleneck. That limits the throughput of the entire value stream. Case studies conducted with advanced technology partners such as Ericsson demonstrate that when organizations introduce agile initiatives without addressing this bottleneck, they merely add more work in progress, increase system congestion, and fail to improve delivery times. The theory of constraints outlines 5 structured focusing steps to manage and eliminate these system bottlenecks. 1. Identify system bottleneck. Locate the single weakest link limiting overall throughput. 2. Exploit the bottleneck. Maximize bottleneck capacity without new investments. 3. Subordinate everything else. Align all non-bottleneck processes to the bottleneck pace. 4. Elevate the bottleneck. Invest in expanding the bottleneck's resource capacity. Repeat. Prevent inertia. Find the newly emerged system bottleneck. These steps are operationalized through methods like software process improvement through lean measurement, which integrates multidimensional measurements across requirements, development, testing, and maintenance to systematically regulate work in progress and balance organizational capacity. This analytical focus on flow is central to lean software development, first proposed by Robert Charette in 1993 as a risk management framework and subsequently synthesized with Donald Reinersten's project development flow theories. Lean software development is governed by 7 core principles designed to eliminate waste and optimize the entire system. Eliminate waste. Identifying and removing any activity that does not directly create customer value, such as partially completed work, handoff delays, or unnecessary features. Build quality in. Preventing defects from propagating downstream by utilizing automated testing, pair programming, and rigorous definition of done. Create knowledge, establishing frequent learning loops through retrospectives, post-incident reviews, and collaborative wiki platforms. Defer commitment, postponing irreversible architectural decisions to the last responsible moment to reduce risk and maintain flexibility. Deliver fast. Maximizing throughput by building simple incremental solutions and obtaining rapid customer feedback. Technical debt. The structural interest of local optimization. Technical debt serves as the structural architectural manifestation of localized short-term optimizations in software development. First conceptualized by Ward Cunningham in 1992, the tech debt metaphor describes how selecting a quick, temporary technical solution to expedite immediate feature delivery incurs a principal debt that must be eventually repaid with interest, or unexpected rework costs. Failing to systematically pay down this debt degrades the long-term maintainability, scalability, and security of the product. A field study conducted by the Software Engineering Institute at Carnegie Mellon University examined how tech debt is perceived and managed in large-scale projects. The study confirmed that while practitioners frequently define tech debt as simple bad code or insufficient refactoring, the most problematic and costly surface of debt lies in architectural choices. These architectural choices, such as coupling monolithic pipelines or selecting rigid database structures, are difficult to correct without a complete system redesign. The CMU field study highlighted a lack of systemic awareness among engineering organizations. This structural debt is compounded by premature optimization, where developers spend excessive time optimizing localized code paths that are not systemic bottlenecks. This premature optimization increases code complexity, degrades readability, and serves as a major driver of tech debt. Under compressed deadlines, engineering teams frequently make localized design compromises that accumulate distinct forms of tech debt. Architectural debt. Deploying monolithic data pipelines to bypass decoupled microservices. This leads to high system coupling, severe scalability constraints, and high cost of redesign. Data model debt. Utilizing basic unpartitioned schemas to accelerate database setup. This leads to severe performance degradation, such as data scales, database repartitioning, requires downtime. Code debt. Writing unreadable, messy code to meet immediate sprint deadlines. This leads to elevated defect density, high rework cost, and slow future feature velocity. Documentation debt. Foregoing the creation and maintenance of architectural decision records. This leads to loss of institutional knowledge, leading to repetitive design errors during refactoring. Infrastructure debt. Relying on outdated servers, libraries, or unpatched software dependencies. This leads to system instability, high operational cost, and severe cybersecurity vulnerabilities. Operational debt. Bypassing proper performance tuning of software. This leads to high data processing latency, elevated system failure rates, and unstable pipelines. Process debt. Utilizing manual error-prone deployments and testing pipelines. This leads to slower deployment cycles, frequent regression bugs, and operational overhead. To remediate these compounding costs, organizations apply structured engineering strategies. Effective tech debt management requires integrating specific tools and processes into the active development lifecycle. Dedicated debt allocation. Allocating 10 to 20% of every development sprint exclusively to tech refactoring, tracking time separately to ensure sustainability. Test-driven development. Incrementally improving test coverage, particularly in high-change problematic areas of the code base, to establish a safety net for future refactoring. Boy Scout rule. Adopting the cultural principle of always leaving the code better than you found it, encouraging minor continuous code improvements during feature development. Architecture decision records, documenting the structural why behind critical design choices to preserve institutional knowledge and support future engineering reviews. Feature toggles, implementing gradual toggle-based deployments to execute major architectural refactoring in small, low-risk, shippable units. Agentic workflows and cognitive debt. In 2022, following the public emergence of large language models, the digital ecosystem experienced a structural discontinuity. This adoption is uneven across digital modalities, with software engineering and visual graphics exhibiting the highest rates of AI integration. Within software engineering, this transition has evolved through three distinct waves. Wave 1, pre-2022, intelligent autocomplete. This is context-aware single-line code suggestions. Wave 2, 2022 through 2024, conversational code generation, synchronous prompt-based chat interfaces like ChatGPT. And Wave 3, 2024 to the present, agentic coding, autonomous multi-step planning tools and pipeline integration. These agentic systems leverage flow-based architectures, planning algorithms, and automated tool integrations to execute multi-file refactoring, run test suites, and manage deployment pipelines with minimal human intervention. While these capabilities have driven immediate localized productivity gains, they've simultaneously introduced new systemic challenges. By automating the micro-level tasks, we've shifted the engineering burden towards macro-level system maintenance and system management, requiring developers to transition from being primarily code writers to code reviewers and system orchestrators. Engineers must define the constraints, quality gates, and automated guardrails within which autonomous agents operate, shifting their focus to systemic architecture and rigorous output verification. Conclusions and recommendations. Localized improvements, whether achieved through functional centralization, manual development shortcuts, or generative AI tools, inevitably degrade the long-term viability, scalability, and security of software systems. True engineering excellence requires a deliberate shift towards whole system governance, where technical choices are continually aligned with global value streams, feedback structures, and organizational objectives. To execute this transition, engineering leaders and software architects should adopt the following actionable recommendations. Transition to flow-based metrics. Organizations should abandon localized output metrics such as commits, story points, or developer activity rates, and manage the software development lifecycle utilizing global flow metrics such as deployment lead time, change failure rates, and work in progress capacity limits. Restructure teams around value streams. To eliminate functional silos and handoff delays, organizations should restructure software departments into cross-functional product teams that possess all the multidisciplinary competencies required to deliver a feature from concept to production. Automate global governance. Transition away from manual phase gate review boards that bottleneck delivery. Instead, institutionalize continuous integration and continuous delivery by embedding security, compliance, and quality checks directly into the deployment pipeline. This shift-left approach ensures systemic integrity without sacrificing development velocity. Govern AI tooling at the system level. Rather than allowing the ad hoc, localized adoption of generative AI or development shortcuts, which often accelerate code generation at the expense of code maintainability, establish systemic guardrails. Evaluate all new developer productivity tools based on their impact to the entire value stream, ensuring they enhance overall system health rather than merely increasing unmanaged tech debt. Manage technical debt as a strategic risk. Shift away from viewing tech debt as an isolated engineering concern and treat it as a top-level risk to organizational agility. Mandate that a dedicated percentage of capacity within every value stream is explicitly allocated to continuous refactoring, architectural evolution, and debt reduction. Ultimately, optimizing for the whole system requires a deliberate departure from traditional cost center mentalities. It demands the courage to prioritize long-term resilience and architectural integrity over short-term localized victories. By aligning metrics, organizational structure, architecture, and governance toward a unified value stream, engineering leaders can transform software development from a series of fragmented tasks into a sustainable, high-performing engine of compounding business value. If you found this video informative, please consider liking and subscribing. Well, that's all for today. Thanks, and take care.